So good afternoon, all of you. First of all, on behalf of the entire operator theory and operator algebra community, let me thank the organizers, Sayan Chakraborty and Srinchan Sarkar, for initiating a web seminar like this, because these kind of interactions or seminars are very required during a pandemic situation like now to keep us active, engaged, and keep going. So thank you for that. So today the first speaker of our seminar series is Professor Rajarama Bhat. I don't think he needs an introduction, but I could see that there are some young or new mathematician among the audience. So for them, maybe I'll just briefly introduce him. So Professor Rajarama Bhat is a professor at ISI Bangalore, and he completed his PhD from ISI under the guidance of Professor K.R. Parthasarathi, another well-known mathematician. And Professor Rajarama Bhat, his research interests are mainly on operator theory, operator algebra, and quantum probability. And his work on dilation theory is very well known and well recognized. So today he is going to speak on his recent work on the same topic. So I think he is going to present a set theoretic version of some of the basic results from dilation theory. Yeah, sir, please. Yeah.
Okay, so thank you. So, well, you have seen the title now. So, so let me begin with these acknowledgements. So this is a joint work with Sandeepan De and Narayan Rakshit. Okay, and I should thank my sponsors, JC Bose Fellowship for research funding. And I would like to thank these organizers for this new initiative. Wish it great success. And I consider it as an honor to be the first speaker. So, first question many people ask is, so why caricature? Why I am using this? So, there is something which this, some indication comes in the center. Just a minute. Yeah, okay. So, why caricature? So, first thing, it is caricature gives sort of simplification, means it is a simplification in the structure, and some aspects are emphasized. Like you saw the caricature of Gandhi. Some things you saw big ears like that, some are emphasized, maybe some are overemphasized, whereas some other aspects are completely ignored. It's not like a photograph or a picture where you try to be true to the original. Some are emphasized, some are not emphasized, some are completely ignored, and that is what is happening here. And so we have setups are different from the original, results are different, but still comparable. That is what it is. Not that one implies the other, whichever way, it is not true. Whatever we have results, it doesn't imply the derivation results, the usual operator theory results, and operator theory results won't imply this because setups are different. So our talk will have sort of three concepts, three distinct parts. One is the single variable operator theory, then multivariable operator theory, okay, single variable, multivariable. Then there are some things, sort of generalizations and variations. Okay, so we are presenting a set theoretic version. So what are the single variable theory results we are talking about? Very basic things like the Wold decomposition, Halmos dilation, Nash dilation, intertwining lifting, etc. And a basic reference, if you are new to this subject, I expect most of the people here know these things, but still, if you are new to this, I think the place to start with is this classic book of Nash and Foyas. There is a new edition where the new authors, Harry Barkovici and Lazu, they have modified things. They have put new things there. So this is a good place to start to read about these dilation theories. Then multivariable theory, we have the undue dilation and commuting and non-commuting dilations of operator tuples. Okay, so good place to look at that is this new, the recent one, dilation theory, a guided tour by Shalit. So it is really new this year, so you can look it up. We also talk about some things like BCL theorem, which are not covered in any of this, but I may give you separate references later. Okay. So then we also talk about some generalizations and variations, some sort of very natural things you can think about, and some vector space versions, etc. I'll speak about it when I come there. Okay. So Wold decomposition. Okay. So in fact, this is not really dilation, but this helps us in understanding dilation, the Wold decomposition. So H be a Hilbert space, and an isometry you take V from H to H. Then you look at first this space H1 is the intersection of ranges of powers of V. So apply H, V of H is a subspace of H, V square of H is a further subspace. Go on, take the intersection. So that's a subspace of H, closed subspace of H, you call it H1. Then you look at its orthogonal complement. So you call it H0. So the whole space breaks up as H0 direct sum H1. But you can observe that these subspaces H0 and H1 reduce V. So V becomes a direct sum. It is a direct sum of two isometries, V0 and V1. The V1, which is the V on H1, that is a unitary. Okay. Whereas the other one, V on the orthogonal complement H0, that's a shift. By that I mean the intersection of the ranges here is 0. Okay, because whatever intersection was there, we removed it and called it as H1. So then we get the Wold decomposition theorem, which says that this H decomposes as this direct sum, and V on H1 is a unitary, here it is, and on the other part, the intersection is 0. Moreover, this is a sort of, we did it, sort of constructed it this way, but you don't have to construct it this way. If you demand this, this is the only way to do it. The decomposition is unique. Okay, so H breaks up as H0 direct sum H1. One part it is a unitary, and another part it is a shift, the pure shift. Okay, the intersection is 0. Okay. Now, so I can get that H0 in a different way also. Okay, the first space H0. So you call a subspace W as a wandering subspace for the isometry if apply V to the power M and V to the power N. So then the intersection should be 0 for M different from N. Okay, for all M and N. Then you call W as a wandering subspace. And there is a canonical wandering subspace here, namely the orthogonal complement of range of V, V of H perp. So that is a canonical wandering subspace. So then you can see that, okay, VW is orthogonal to W because this is in the range. This is the orthogonal complement of the range. Then you can see that this is yes. Someone asking something? So it breaks up like this. It's a direct sum. Okay, so this becomes H0. So this is another way of constructing H0. Okay. Now we would like to have a set theoretic Wold decomposition. So just take a non-empty set A and an injective map. So there is no Hilbert space, just any old set and an injective map. So you define a subset W as wandering now. Okay, just like before, but the intersection is not orthogonality, but the intersection is empty set. Earlier they were orthogonal subspaces. Now they are disjoint subsets. Okay, then you call it wandering. So an injective function V is said to be a shift if the intersection is 0, just like before. So then we have this theorem. A be a set and V be an injective function. Then A decomposes uniquely as a disjoint union where A0 and A1 are left invariant by V like before, and one part it's a shift, another part we had unitary before. Now instead of unitary we have a bijection, right? So that is a natural analog of unitary. Okay, how do you go about proving it? You just take like before, take W as the range of V, the complement, And then you can see that it is a wandering subspace. Just give a two-line proof. You take any A in the intersection of, say, VMW and VM plus KW for some M and K, then A belongs to this intersection. So it belongs to, since V to the power M is injective, so the only way it can happen, like this is equal to this as well as this for some W1, W2. And since V to the power M is injective, it means that this W1 has to be VK W2. So, but this is not possible because W1 is in the complement of this range of V. So only way it is possible is K equal to 0. Okay, so that means this K has to be 0. So if they are distinct, then they are disjoint. So that shows that W is a wandering subset. Very elementary. So A0 you take as these are all disjoint sets, the union of them. Take A1 as the complement and you have the result. Okay. So this part is a shift and the other part becomes a bijection. And that is the only way to do it. So here is the dictionary. So Hilbert space has become set. Bounded operator has become just a function. Isometry has become injective function. Unitary gets replaced by bijective function. Orthogonality becomes just disjointness. Okay, so natural correspondences. So I would like to have a decomposition of these injective maps. Again, we go back to the Hilbert space operators to see what is happening. In the old decomposition, you have an isometry. Right? It becomes a direct sum of pure isometry of the shift and a unitary. Okay. The pure part or the shift part, you realize it as unilateral shift with some multiplicity. So you see, you have the wandering subspace. You can take the natural, the first, the sort of canonical wandering subspace. You take a basis for that. From that, you see that when you act V, it keeps shifting to the other part. So it gives you the multiplicity space. The canonical wandering subspace gives you the multiplicity space. The whole isometry, pure isometry, or the isometry part is just the shifter in L2Z plus with some multiplicity. Okay. So the pure part is very easy to understand. So basically there is only one example there, namely the unilateral shift, but it can come with some multiplicity. What about the other part, the unitary part? That you have to understand using the spectral theory. Okay, so there you have the spectrum on the circle and you have to apply the whole machinery of spectral theory. And if you want to understand it fully, you have to go to understand the multiplicity there. So you have to go to Hahn-Hellinger theorem and all that. So in fact, that part is actually more complicated. It's the pure part, which is very simple. There is just one example, namely the unilateral shift here on L2Z plus with some multiplicity, which now this you may also realize it as multiplication by Z on the Hardy space with some multiplicity, just to get a function theoretic flavor. Now we would like to do the similar thing for these injective functions. So what do we do? So you have taken injective function. For A and B in the set A, I will write A is equivalent to B, okay? Or you can go from A to B, I will say. If A is some power of B applied to B, or B is some power of B. So from B, you can go to A by applying V, or from A, you can go to B, okay? One of the ways, okay? It can be both. If either this way or this way, then you say A is equivalent to B. So that's an equivalence relation on A. So the corresponding equivalence classes are known as orbits of A. Okay, so you just have the orbits. Okay, two elements are equivalent if we can go from one to another by applying V a few times, a finite number of times. So what are injective maps with exactly one orbit? Okay, so here are the examples. So cyclic permutations, for instance, we take a D and take ZD like this. I'm including Z1 also, just the singleton 0, and just the cyclic permutation. Z1 just gives you the fixed point. So that is one type of example. Then bilateral translation, like you from Z to Z, you just shift Sn equal to n plus 1. Okay, I don't want to call it a shift because the intersection of this is not empty. So I would like to call only when the intersection is empty to be a shift. Okay, so I'm just calling it as bilateral translation. So then S is bijective and has single orbit. Then unilateral translation. Okay, in Z plus we have the shift. So this is like the shift we have in the L to Z, right? L to Z plus, the shift operator we are familiar with, unilateral shift. It is exactly like that if you just look at the basis, some natural basis. So any injective map with single orbit has to be one of these type, right? Either a cyclic permutation or bilateral translation or unilateral translation, unilateral shift. So it will be bijective correspondence with exactly one of these. Okay. So now I want to have multiplicities. Okay. So like the bilateral shift on Z, you can put some multiplicity. That means you look at X cross Z for X being some other set, and you apply the shift only on the second part. In the first part, you keep it same. So this is 1 cross S, okay, 1 on X, so the identity map on X, and the shift on the second space on the Z. Same way, you can have cyclic permutations with some multiplicity, or the unilateral shift with some multiplicity. Okay, so all the earlier examples, you can have them with multiplicity. Now, any injective map from any non-empty set A to A, you just think for some time. You see, in each orbit, it would look like one of these, but either bilateral translation or cyclic permutation or unilateral shift. So in every orbit, it looks like that. So if you collect together the similar things, you get the multiplicity spaces. So you get the equivalence classes and you multiply. So I guess you can understand. So the whole space, this A will be in bijective correspondence with this B and W, where here, see, these are cyclic permutations with some multiplicity. So the multiplicity spaces can be different for the different types of shifts. Okay, then you put them together. So any injective map would be equivalent to this. I feel like telling unitarily equivalent, bijectively equivalent to this. Okay, so that is how general injective map looks like. Okay. So now I go to proper derivation theorem. Okay, the first derivation, the basic, most basic derivation result is the Halmos derivation. So you take, I have to, T be a contraction. I missed the word contraction. Put the word contraction here. Let T be a contraction on a Hilbert space. Then the Halmos derivation is on H direct sum H. Okay, so that is a unitary on this. Okay, given by this. So I suppose most of you are familiar with this, so I don't want to spend too much time on that. So T is a contraction, ensures that I minus T star T and I minus T star are positive. So you can take their square roots and you put, these are the so-called defect operators, and construct this unitary on H direct sum H. You have to verify that it is a unitary. So what is it saying? What does Halmos derivation say? Any contraction T, you can sort of enlarge to a bigger space where you have a unitary. So every contraction is sort of a restriction of a unitary. Okay, and this bigger space is natural one, H direct sum H. So you may identify the original H as H direct sum 0. So I'm just writing the same thing in a different way. So identify the original H as H direct sum 0. Then U acting on H, the first part, first copy of H, restricted back to H is T. That is what this corner is T. And that you write it this way. So apply U on the first copy of H, then compress it back to H. So that is T. So this is another way of writing the fact that this corner is T. Okay. So this is a sort of most basic dilation result. Every contraction T can be dilated to a unitary. So it is very important here that what we are doing, it's very important that here there are three parts to the dilation. First is that you embed original H into a bigger space as H direct sum 0. Okay, so your space H is embedded here. Then you have a map there, a nicer map on the bigger space. Here it is a unitary. Sometimes it can be isometry, sometimes it can be a homomorphism, whatever. Some nice map on the bigger space. Then you compress it back to H. So the three components, the first one is the embedding of the original into the bigger space. Then a good map there, a nice map on the bigger space. Then a compression or another map, which is an idempotent. So where does this map, compression map, pH map? It maps into wherever the original space has been embedded, right? This H is embedded here. So this will map to that, okay? And it will satisfy P square equal to P. That will have to be an idempotent all the time, okay? So similar things appear in various dilation theories, like in Markov processes and such things. This compression, this one idempotent will be an expectation map or a conditional expectation map, like that, okay? So the three components are there. So once again, I emphasize the three components are embedding, then a good map, and then followed by a compression. So that is what we would like to have. So let us see Halmos dilation for functions. So you take a function from A to A for some set. So you need two copies of A. You just take Cartesian product with 2-point set 0, 1. So these are two copies of A. Then embed A into the first copy. I of A is A, 0. Then I want a bijection on the bigger space. So natural bijection, you send A0 to A1, A1 to A0. Okay, just interchange the copies. So then I is injective and U is bijective. Then I want a compression on the bigger space, which maps to B to B, right? So here it is, P from B to B. So if it is already A, 0, you keep it as it is, okay? So the range of I, okay, where the A has been embedded, there it will not do any change, okay? And the other part is HA, 0. Then you can see that P is an idempotent, P square equal to P, and the range of P is the image of A, okay? The wherever A has been embedded. So the dilation consists of three parts. The one is the, of course, you need a bigger space B, and then the embedding I, the bijection U, and project it back by P. Okay. Is it okay? So, oh well, we need the dilation property, right? So here is the dilation property. Okay. So you sort of identify A and I of A. Okay. So then, so A is embedded as I of A. So on that you apply U and compress it back by P. It should give you back H. Okay. So this is exactly like the equation we had previously, T as a compression of U. Okay. Just the same thing. Now the function H is the compression of this bijection U. Okay. Apply I, then U, the bijection, then compress it. Okay. So this will be the general feature. Okay. So then the most famous theorem, okay, the most basic one is the Halmos dilation, but the most famous one, the most useful dilation result is the Nash dilation. So here it is. So let T be a contraction on a Hilbert space H. So then there exists a Hilbert space K containing H with an isometry. Okay. You can do it unitary. I'll come to that later. First, I want to look at the isometric dilation. Okay. So you want to have an isometry here where powers of V, you restrict back H, you get T to the power N. So this is exactly like the Halmos dilation, except that now you have it for all N, all powers of V. Okay. And you get back all powers of T. So we often call it as power dilation, okay, or Nash dilation. Okay. So this is the most natural result. So any contraction can be dilated to an isometry like this. Moreover, this pair can be chosen to be minimal. That means the span closure of V to the power N H or H. So that is the whole space. So H has been embedded in the bigger space, right? So there, if you apply V, wherever the space gets covered, that span closure should be K. So that is minimality. And then we have the theorem says that this kind of minimal derivation K and V is unique up to unitary equivalence. So I will not go to the proof. Instead, I would like to have this kind of derivation for functions. So here is the Nash derivation for functions. Just the definition. You take any non-empty set, and so I will call it injective power derivation. So I need three things: a bigger set B, and three things there: the embedding I from A to B, an injective map, and the isometric derivation I want, right? So isometry is replaced by injective map. So a V from B to B, and you should get back an idempotent, and P of B equal to I of E. Okay, and this P should have this property. Okay, so this original function may not be injective, but you derivate it to an injective function. So there is nothing like contraction here because we have no norm, right? Just any old function, you are derivating it to an injective function. Okay, so this is what we want. Okay, so you want a set B, an embedding of A inside B, an injective map there, and compress it back. So an idempotent, and we call it a minimal derivation if the B is the union of this. Now there is no span closure, just the union, set theoretic union of the ranges of this. Then we call it minimal. So can we do, so two derivations we said to be bijectively equivalent, like unitary equivalence, if there is a bijection from one to another, which maps the corresponding things. I prime, I gets mapped to I prime, V goes to V prime, like that. Okay, so natural thing. So this is just a definition. So you ask the question, is it possible? Well, it is possible, and here is the construction. I give you 2 minutes to see the construction. This I call as the standard derivation. Okay, so what do? You take this A, Cartesian product with Z plus, embed A as A comma 0, the first copy of A. V is just the shift in the second copy, and P, you compress everything to the first copy by this, because we want the compression to the image of A, right? So this is the only possibility. Well, so this works, and this is a minimal derivation. Okay. So I'm calling it a standard derivation. You will come back to this again and again. Okay. This is sort of most natural derivation here. Okay. So we have the theorem. Every function admits a minimal injective power derivation, just like Nash derivation. Okay. Oh, sorry. Sorry, I went back, I guess. Okay. So this is an injective power derivation, and it is minimal. So I have said this. So there is no uniqueness here in that as it is, right? The standard derivation, in a sense, is not optimal. So it is minimal by our definition, but it is still not optimal. In what sense? Like if our original map H is an injective map, then still this derivation will give some bigger thing. Okay, it will not be just the same H. Okay, even if the original map is injective, that should not happen, right? So we try to mend it. So here is a definition. A subset D of A is said to be defect space for H if H restricted to D complement is injective. Okay, so then I call it a defect space. On the complement, it is injective. So it sort of measures, the defect space measures how far the function is from being injective. Okay, and you call it a minimal defect space if there is no proper subset on which is a defect space. Okay.
Do you want this D complement to be invariant?
Yeah, here is the comment. we don't insist that the complement is invariant. Okay, we do not insist that, but on that part it is injective. So every function admits a minimal defect space. You can check that, and a minimal defect space is empty if and only if the function is injective. Okay, so you can make it very small if it is injective. Okay, so there is no need to dilate the function on the injective part. Okay, on the defect, the complement of the defect space. So that is what we do. So here is the dilation using the defect space. Okay, again few minutes. So on decomplement, there is no need to do the dilation. So there you just keep it 0. Okay, just to embed it. On the other part, we have to do the dilation on the defect space part. On the defect part, you have to do the dilation. If you are familiar with the Nash dilation or the multivariable Popescu type dilation, you will see this kind of this. The defect space, you need copies of the defect space. Okay, and the other part, you don't have to do anything. So that is what happens here. On the complement, you keep it fixed. On the defect space, you need Z plus many copies of that. And the embedding as before, and the injective map doesn't do anything on the complement of the defect space. It's just H of H, and the other part is the shift. And the same thing works, and it is a minimal injective dilation. Okay, so with every defect space you can do this. So, and it is the same as the standard dilation if you take the whole space as a defect space A. Okay, complement is empty, so you can do that. So we want then talk about the uniqueness of the dilation. You see another property. We need to look at another property. If you look at the Nash dilation, the minimal isometric dilation of V, it has a special property. This V leaves H-perp invariant. Okay, that is seen, and it's a very important property. It comes in various dilation theory results. We use it. We need it. That this V leaves H-perp invariant. So I would like to have a similar thing. An injective dilation, we call it co-invariant if IA complement is left invariant. So if you are, see, IA is the copy of A. If you are out of that, if you are outside that, then we don't come back to I of A. Okay, if you are outside of A, then we don't come back to A. That is the co-invariance. Just like this, H-perp is invariant. Okay, then you call it co-invariant. Okay, so here is the theorem. So you take a co-invariant, so that is the additional property we need to impose. You take a co-invariant minimal injective dilation. Then if you look at the vectors which are going out of A, that is the defect space. That is becomes a defect space for H, and every such co-invariant minimal injective dilation is equivalent to one of these. So all such dilations are given by some defect space. Okay, so the dilations are here are parameterized by defect spaces. Okay, so next is the pure maps. Okay, when you look at the dilation, see there is, you get dilate the contraction to an isometry that breaks up into two parts, the unitary part and the pure part. You want to know when the unitary part doesn't exist. Okay, unitary part is not there, only the pure part is, the shift part is there. So that happens if the contraction is pure. That is T star to the power n converges in strong operator topology to 0. Okay, this is the usual Nash dilation thing. The result is the minimal isometric dilation is a shift. That means the unitary part is not there if and only if the contraction is pure. But if you look at the isometry V, it is pure if and only if it is a shift. Okay, that one can check. Now we want to have similar thing for functions. See, this equivalence is not true for contractions. For contractions, the intersection of the ranges is 0, then it is T is pure, but the converse is not true. You can just take the example of this scalar times, just the scalar multiplication by T between 0 and 1, then you can see this is true, but it is still pure. Okay, so the purity here, if you want to think of in this way, that is true only for isometries, not for contractions. So here is the theorem. So you look at, so as I said, these minimal co-invariant dilations are parameterized by defect spaces. So on the defect space or the complement of that, so I am characterizing as to when is the dilation a shift. The dilation is a shift if and only if on this part, this is pure in this sense. Okay. Of course, if it happens for the whole space A, then it is automatically a shift. But that need not happen. It may happen only on D complement. I have a small example here, which says that you see this part when on the whole of A this is empty. So then one can show that this is a shift even without having this assumption of co-invariant. And such dilations are possible. Here is one such example. I think since I'm running short of time, I will not go into that detail. Okay. So then is the intertwining lifting theorem. The intertwining lifting theorem of Nash and Foyas is well known. The commutant is the lifting theorem, is a special case of that. And this result is very popular. It has many applications. So what is it? Here is it. So you take two contractions, okay, and their minimal isometric dilations, okay, which are unique up to unitary equivalence. Suppose you have an intertwiner, okay. So these are even on different spaces. You have an intertwiner, you have an S from H to H1, which intertwines in the sense like this. So then that can be dilated or lifted to an intertwiner of the dilations, okay. So there is an operator R from K to K1, which intertwines, okay, with some additional properties. But the main thing is that the intertwiner at the level of contractions are lifted to intertwiners at the level of minimal isometric dilations. And the converse is also true. Okay, if you have an intertwiner at that level, with these additional conditions, then you can compress it back and you get an intertwiner at the level of contractions. Okay, so the intertwiners can be lifted. So we want to have intertwining lifting for functions, and that is true. So here also we have two functions instead of two contractions and their standard dilations. And then here I'm just going fast to say that the same thing is true. That is, you here S is an intertwiner between H1 and H2, these functions. Then you look at the standard dilations for both H1 and H2. There will be an intertwiner function like R. Conversely, if you have an intertwining function at the level of dilation, then you can compress it and you will get, so it is means very nice, means it's a perfect analogy here. Okay, but here I have done it for the standard dilation. You can also do it dilations with defect spaces. Okay, so then there is some, this S, the intertwiner has to have some properties with respect to the defect spaces, but sort of very natural conditions. Then you get an intertwiner at, means at the level of dilation. And the converse is also true. So intertwining lifting can be, you can have an exact copy here. Okay. Another result, Sarason's lemma. Okay, what is Sarason's lemma? See, we see that when you dilate a contraction T, you get an isometry V, which leaves H co-invariant, and all the powers of V restricted back gives you powers of T. So the question asked here, you start with V, look at some subspace, your compression to a subspace. When does the powers of V compressed gives you the powers of T? Okay, the powers are respected when you take the compression. So for that, we need not leave the subspace H co-invariant. What Sarason says is that as long as the subspace is difference of two invariant subspaces. Okay, so there are two closed subspaces, M and N, both invariant under V, and H is the difference of. See, if I have this N to be the whole space and this N is, means the H perp, then you get H, okay, H perp and the whole space. So that is a special case. The co-invariance case where you have the Nash derivation, that is a special case. So in general, if you take difference of two co-invariants of spaces, then if you compress V to the power n, you get the compression of V, the power of that, okay? So this kind of power relation is retained whenever you have difference of invariance of spaces. That is Sarason's lemma. So now if we try to do that for injective maps, we have only a partial result. So we know that same thing is true if you have difference of two invariant subsets, okay? See here, I have to define what is P. That is, here when you have a subset, it's a natural, you have a natural subspace, you have a natural projection. But here in this case, just because you have a subset, you don't have a canonical P. You have to define a P, but you say that there exists a P like that, P square equal to P and P of B equal to A, satisfying this, okay? So whenever you have a difference of invariant subsets, it is okay, but the converse is not true. So Sarason's lemma, we have only halfway, not full, okay? So the converse is false. I have a simple example, but again, I will skip the example, okay? We'll go to something else, the unitary dilation. So Nash dilation, instead of isometric, one can also have unitary dilation. Same thing can be done here. Instead of injective function, you can dilate to a bijective function, okay? So this is the statement of the theorem, saying that if you have a function, you can dilate it where you have a bijection, okay? Other things are all same, like before. It's just that the minimality is also there, okay? So, and it is possible. The construction is simple. Instead of Z plus, you take Z. And the shift on the second copy, everything is identical. Only problem is this P, how to define it for when n is negative. It's quite arbitrary, okay? You can define it like this, but it's rather arbitrary. So there is some non-uniqueness in this unitary dilation, okay? Or the copy of the unitary dilation, okay? Or I can say mimic of the unitary dilation. It doesn't work very well. And it is not very surprising. Actually, the Nash unitary dilation, I think, is just by chance. It's the isometric dilation, which is much more natural, which, I mean, so many natural dilations, like for when go to CP maps, you get endomorphisms as dilations, not automorphisms in general. So most natural thing part is the isometric dilation. Okay. Next, now we go to multivariable. Okay. So the dilation. Okay. So dilation. So here is a statement. You have commuting contractions. You dilate them to commuting isometries, so that you have different powers compressed back. You get the different powers of T1 and T2. This is dilation, very popular. So, and we know that it cannot be extended to more than 2. So we would like to have dilation here, and it is possible. And the surprise is that it can be done not just for 2, but for as many as you want. Any indexing set J, I can start with the commuting family of functions. I can dilate them into commuting injective maps. Okay, and that is possible. So dilation, there is no restriction now. Instead of 2, you can do it for as many as you want. And this is just a statement as to what I want for. These are very natural things. We just mimic the thing and we say that it's possible. Okay. And here is the construction. I will not go into the details. I have written it down, but I think there is no need. It is a very natural construction. Instead of earlier we had just a Z plus, then you look at Z plus J. So this is the space for all the indices. You need a copy of Z plus, and you embed everything as 0, where 0 is a 0 function. And now we have the shifts in each copy like that. We have standard commuting dilation. Very natural thing, you just copy and it works. Okay, and you get a minimal commuting dilation. And the same thing you can do with the defect spaces also. Okay, so we just need appropriate modifications, but there is something small change is needed. here, when we do defect spaces, I need this D complement to be left invariant by all Hj. See, we remarked in the beginning, didn't need this complement to be left invariant by H, but if you just to ensure commutativity, now I need that. Okay, so that is an additional thing you need. Okay, so once you have that, it is fine. With defect spaces also, one can do the dilation for the commuting dilation. Okay, and here is the construction. The similar to the earlier thing, you decomplement only 0, the rest you make the copies, and the same thing works. Okay, so let us skip that. So non-commuting dilation. So again, famous results of Bunz, Frazo, and Popesco. It's not joint paper. The separate results of Bunz, Frazo, they did for I think pairs. Then Popesco, the multivariable version. You take a what is known as a row contraction, T1, T2, Td, as a row forming a contraction which is equivalent to this condition. So then you dilate them to isometries with orthogonal ranges. So non-commuting case, so you don't ask them for commuting Vj's, but we need some property. If you don't put any property on isometries, it's very easy to get dilation. But the property, the right property is that they have orthogonal ranges. Okay, Vi star Vj is delta Ij. So you dilate a tuple T1, T2, Td as V1, V2, Vd with orthogonal ranges, and that is possible whenever this condition is satisfied. And there is a minimal dilation, and it is unique. Okay, so this is what we mean by dilation. All copies of T you should be able to recover by corresponding products of Vj's. Okay, there is a minimal isometric dilation like this, and it is unique up to unitary equivalence. Okay, as long as T1, T2, Td forms a row contraction. So we can do the same thing for functions. So you take, now what is orthogonal ranges? So that has to be changed to sort of disjoint ranges. Okay, so we want disjoint ranges now. Okay, so that is the definition. Instead of orthogonal ranges, we want disjoint ranges. The rest remains same. Okay, it's just that change, and the minimality dilation, there is no change. Everything else is same. Just the orthogonal ranges has been replaced by disjoint ranges. And so we have a basic theorem. Every family of functions, no condition. Okay. Earlier we had row contraction. Since we don't have norm, like before we didn't have a contraction, nothing. And any family of functions, you can dilate them to minimal, injective, non-commuting dilation. And the construction is again something which looks like the Fock space, like in the case of operators. Okay, you can write down the dilation sort of explicitly. Okay, in a natural way. Again, this is sort of the standard part without any defect space. With defect spaces also we can do, but again there are some small twists. So we need a sort of joint defect space. Okay, so different J and K also. Okay, so another way of putting that, if you form a sort of a composite function from J cross A, if you do this Hja, then that should be injective on J cross D. Okay, the injectivity of each Hj's separately is not enough. I need the injectivity of this function, which is formed out of all the Hj's. That should be injective. Okay, on D complement. That is what it is. So if you have such a joint defect space, one can do the non-commutative derivation. Okay, so I'm going a bit fast, but I don't think you are losing much. It is just to, the moral is that whatever you have for operators there, we can do the similar kind of derivations, both the commuting case and also non-commuting case. In commuting case, it is even better because not for just for two, but for any family. And only thing you have to be careful is about some small changes in the defect space definitions and modification, the requirements on the defect space. Okay, otherwise everything can be mimicked. Okay, so here is the construction. Again, I don't want to go to the details. because I think it's better I go to the BCL theorem. Okay. So here is the BCL theorem of Berger, Cowan, Lego. So it describes the structure of, so I have done now the single variable and multivariable. Now the BCL theorem is for the pair of, so for commuting isometries. So we are following this presentation here, where this BCL, their result is rather old, so, and it's difficult to read, so you can look up this to a nice presentation. And here is another reference where this has been used. And what is the theorem? So you look at commuting isometries on a Hilbert space. Okay, by the Wold decomposition, this V, you have the apply Wold decomposition for the product. So we have two commuting isometries, V1 and V2. Look at the product. The H decomposes as H0 direct sum H. So one part is unitary, other part is shift. So it's just the Wold decomposition for the product. See what it means for the V1 and V2. Okay, here I just said that the one part on H0 you can think of as multiplication by Z tensor identity. The pure part is the standard shift with some multiplicity, and the multiplicity space can be thought of as V of H per. It is the Wold decomposition. Just here I have nothing more than the Wold decomposition for V. See what does it mean for V1 and V2? Now V1 and V2 commute. So that ensures that this H0 and H1 reduce V1 and V2, and they themselves decompose. These isometries V1 and V2 also decompose like this, but it may not be Wold decomposition for V1 and V2. Okay. So here, when you see the unitary part, wherever there is a unitary part of V, these V11 and V21, they become unitaries. So they become commuter unitaries. So this part you don't have to worry. But in this part, V10 and V20, they may still have some unitary part. They may not be pure. Okay. So the BCL theorem describes what happens there. Okay. So it says then that where do I? Okay, here it is. Okay. It tells you that up to there is some unitary. Okay. Forget that. Other part is S tensor P, S is the shift, plus I tensor I minus P. So there is a pair, okay? One projection and a unitary. So the V1 and V2 can be described to a projection and a unitary. There is a natural decomposition of V1 and V2, okay? One part P is the shift and the identity. The other one V2 is the other way around, the identity and the shift. Okay, up to this unitary, it breaks up like this. S tensor P and the identity here, or I tensor S, okay, with respect to P and P per. Okay, so conversely, any such pair would give you a commuting isometries like this. So we want to do the same thing for functions, and it tells you how exactly it goes. So you have a non-empty set and an injective map, so where V1 and V2 commute. Okay, we do the same thing. The commuting thing. We do the Wold decomposition for V. Okay. So I am explaining here what the construction tells you. The same kind of argument, what was there before, you can see that if you see this intersection or the unitary part in there, that is left invariant under V1 and also under V2. And some two lines of argument, like before, on this intersection, on the A1 part, both V1 and V2 are bijective maps. Is the other part which is the interesting part. Okay. So you look at the product V1, V2, do the Wold decomposition, which we have done for functions, apply that. You get A0 and A1. On the A1 part, or the unitary part or the bijective part, V1 and V2 leave that invariant and they are commuting bijections. So other part is also left invariant, but there they may not be pure shifts. So there, that is the part we have to understand. So now, I can ignore the bijective part. So I assume that V is a shift. Okay, so that is the intersection is empty. V to the power n a intersection is empty. Okay, look at the wandering subspace. W is a wandering subset for V. We have seen this. Take Wi, okay, the corresponding wandering subspaces. What is the relationship between the wandering subspaces of V and that of V1 and V2? So here is the basic thing. Okay, this wandering subset for V, you can decompose it in two different ways. It is a disjoint union of W1 and V1 acting on W2, or you can also decompose it like this. Okay, this is the thing which we taken from that paper of Sarkar and others. So the wandering subspace you can break up like this, okay, in two different ways using V1 and V2. Okay, so now you get a bijective map from one to another. Okay, in the operator case, you had a unitary from here to here. Okay, now you get a bijective map from one to another. So the bijective map is explicitly defined. Is this U of W1 is V2 of W1, U of V1 W2 is W2. So the whole space, okay, let me go. The whole space, once I assume that V is a shift, breaks up as a disjoint union of copies of W. W, V of W, V square W. So if I understand what is happening in W, it will tell you the whole story. In W, you get a bijective map U like this. And then you sort of extend it to the whole space. Okay, that requires some notation. Let us, since I'm running out of time, so I will not do that part again. But you see that the A is decomposed like this, and each part you have a copy of U, and you put them together. And if you put them together, finally, what do you get? Here is the theorem, which BCL for functions. It is exactly like before. Instead of direct sum, you had a projection. So instead, you have a subset and its complement, and one part it is identity, other part is the shift, and here it is the other way around. Okay, written the same way, but yeah. And unitary U is replaced by a bijection. Okay, so that is what it is. Okay, you have a BCL theorem for functions. Now I just spend 2 minutes on generalization and variations. So we consider derivations for a map with n belonging to Z plus. So instead of Z plus, we can consider R plus or a general monoid. May I take 5 minutes more?
Yeah, sure, sir. Yeah, sure.
Okay, just 5 minutes. So instead of Z plus, I can take R plus or a more general semigroup or what is known as a monoid. So monoid is an associative binary operation is there on S with an identity element. So it's a binary operation. I am calling it as a multiplicative notation. The identity is not 0 but 1. Okay, and the associative operation need not be abelian. So something like R plus or anything else. So the derivation theory of operators on these general monoids have been considered by many authors. And whatever we have done now for set theory and functions, instead of Z plus, we can do it for in this kind of general setting. We change the semigroup. Instead of Z plus, can have a general monoid. And we just do the standard derivation theorem here. So S is some left conservative monoid. Left conservative means you can cancel from the left. AB equal to AC means B equal to C. Okay. So suppose A is a set and you have a family of functions there which respects the composition with respect to composition. Like instead of h to the power n, I have h at s which respects the composition. It's like the semigroup of operators. So then you can have a derivation. Okay, this is the standard derivation. Whatever we had before, a copy of that in this kind of general setting. So here is the construction A cross S. So earlier I had Z plus. Same thing. You take the Cartesian product with the monoid S now. The embedding embedded to with the instead of 0 now 1 is the identity element. So embedded there, you have the shift. Okay, in the second copy and the projection or the idempotent. Okay, so where do I need this left conservative property to ensure that these VSS are injective I need that left cancellation property here. You can cancel from the left. So once you have that, then this VSS become injective. So the theory can be extended. Okay. Another way, instead of working with sets and functions, we can try to develop the whole dilation theory working with vector spaces and linear maps. So now Hilbert spaces get replaced by vector spaces, bounded operators by linear maps, isometries by injective linear maps, unitaries by bijective linear maps, direct sums by direct sums of Hilbert spaces by direct sums of vector spaces. So you change to a setup of vector spaces and linear maps. And here too, we can have a formal definition. Here is a sample, okay? A vector space and a linear map. Again, there is no question of contraction. And you have a dilation to an injective dilation. And that can be done where, again, this is the dilation property what we need. You can define minimality, everything in the setup of linear maps on vector spaces. And we have the theorem, every linear map on a vector space admits a minimal injective linear dilation. Okay. So no isometry, but injective. Okay. And the construction is like the standard construction. Here is the construction. You have maps from Z plus to A, which are 0, except for finitely many points. And the strange thing is this idempotent P is defined something like this, like a series, but it is a finite sum because after some stage these are all zeros. Okay, so it looks similar to our standard dilation, but is different because there is the addition coming in the definition of P, which was not there before. So though looks similar, but is still different. Okay, so well, you can try more variations. So I don't know. So we leave for other settings. If there is some, we would leave it to the listener. If there is something surprising, please let us know. Okay, thank you.
Okay, so it's time for questions and comments.
Sir.
Yeah.
Sir, I have a question regarding this Sheffer matrix dilation. Sir, as we know, as an if U is a unitary operator, then U can be written as e to the power IA, where A be a self-adjoint operator.
Yeah.
So, sir, is it possible to construct a self for given a contraction? Is it possible to construct a self-adjoint operator A such that e to the power IA be its unitary dilation?
No, it doesn't work that way. No. Instead of giving a contraction, if you have a semi-group of operators, then you can dilate them to isometries. Okay, if you have a TT instead of T to the power n, if you have TT, then you can do. But starting with the contraction, how can you take logarithm to write it as a power? No, I don't see how you can do that.
Okay, sir.
Means your contraction may not have any square root. So
okay, sir.
So I have a question.
yes.
Yeah, so just like an isometry can be extended to a unitary, is there an analog here? Maybe it's easy.
Yeah, I guess injective maps you can extend to unitaries. It should not be a problem. But what else you need there, I think one has to look up. But
it has not been worked out, is it?
I have not thought about that. But we do it here. Yeah, no, I guess nobody has thought about, but it should be possible.
I see.
Yeah, it should be possible.
So by dropping all these fancy structures on a set, you get to sort of dilate just any function. No,
yes,
I mean, yeah. So that's good thing. So so any function can be dilated to an injective map.
Yes, yeah.
So what sort of consequences that you get out of it? I mean, I'm talking about, I mean, one thing that I have in my mind is maybe it doesn't make sense here because of the norm thing involved. It's von Neumann inequalities I'm talking about.
Yeah. In fact, we don't know. We don't have any such thing. This is the first, just a very recent paper. We don't have any such thing. Like, I have no idea what should be an analog of characteristic function, for instance.
Ah, right. Yeah, that's one thing to look at.
Yeah, characteristic function. What does it mean here? I don't know.
I see. But you do have a like Halmos dilation, right? I mean,
yes.
Halmos sort of.
Yes, Halmos dilation. That was simple. That was easy. That's the first thing I did. Just 2 copies, right?
Yeah, I mean, so the Halmos characteristic function is obtained from the Julia-Halmos matrix by plugging in
I don't
the
know.
coefficients.
I'm not familiar with that.
Yeah, so I was thinking of a unitary colligation
So
transfer function thing.
dilation.
Right.
Yeah, characteristic function. I have no idea what it is.
I mean, can you given a bijective function, can you sort of in a canonical way construct a function out of it? Just a function.
I mean, you have to say what property you want from that, right?
Yeah. Right.
Yeah.
Yeah, that's
we
all.
have not worked further from this. We have this
I see.
there in the archive.
Yeah, I had a look.
We haven't done anything after that actually on this.
Right.
Hello, can I come in for a while?
Yes.
Yeah, Rajata, I'm Ved here. Hi.
Yeah, I can see.
Thanks for this talk. I had a very nice query, like being an operator algebraist, what motivated you to, have this dictionary from operator theory to set theory actually?
Now, many a times I felt I am doing the same computation in different times. So like when you work with the shift, for example, isometry, often you work with the basis. So then you are basically working in the countable set. You are looking at the shift there, right? So I thought, why not I forget about this orthonormality and just look at the set itself.
Okay. Because this is
means it gives a sort of the skeleton of the whole thing.
Achha. This is the first time I'm hearing you, giving a talk of this completely different flavor actually. So I thought, what was the motivation, Yeah, might be you have
motivation is to understand the derivation theory better.
Okay. Yeah, then might be, I don't know, since you have taken it to such a general level, might be this can be taken to other categories also.
Yes, very much possible.
Results.
That is what I said at the end. That is, I leave it to listeners to move it to other settings where maybe similar things work.
Right. For instance, I can at least get a feeling that in C-star tensor categories, might be most of these things can be taken care of, because you see from whatever we do in the Hilbert spaces and the operators, isometries and all those things, they have their analogs in the C-star tensor category.
Yeah.
And who knows, might be this can be done there.
Maybe possible, I don't know.
No, it was just a comment. Okay. Yeah, thank you.
We have gone towards more simpler settings rather than more complicated settings.
Okay. That's true.
May I ask something?
Yeah, sure.
Archer, very nice talk. So going to the theoretical setting. Now, one question, because roughly speaking, you don't consider any kind of topology or even measurability issues are no longer around.
Nothing, yeah.
Are there some results where one has to expect a difference? So I'm always wondering what happens with ergodic properties, or mixing properties or things like that. So where one has even in the operator algebraic setting, where one has some very strong toolkits available through fixed point characterization results. So will they all be void in the or?
Yeah, as I said, we have not really thought about other settings. We have not really worked, but and we haven't done any kind of mixing study, nothing. So this is the first one. So we hope it is useful in some other settings also, but we haven't really done any work.
Yeah. So
this is a sort of general framework.
Yeah. So it always goes back to the category or the precise notion what one means now with a dilation, because right now what you look at is the dilations on the level of, let's say, a category of sets and contractions as morphisms. Yeah.
Yeah.
So let's say injections now, injective maps, or so to formulate that more in a categorical sense that one sees where one's really working on, because for example, when you add more things, if you like Kümmerer is doing that, or Arundhati and I are looking at that, in that context of Markov dilations, there one even knows that not every Markov operator can be dilated. Yeah.
Yeah.
So that's so where comes in this difference? So what this is pointing this direction. What also you are asking, you try to understand deeper the dilation theory, yeah, and some things work always, no matter what. Yeah. And but what makes things to break down? Yeah.
Yeah.
So did
some
you see
things break down, but yeah.
Down or
yeah, some things do break down, like the Sarason's lemma we could not do. There's a problem. It doesn't work. Okay. Some things do break down. Many things work. Many things become simpler and easier to work. But as I said, we cannot prove any of those results using the operator theory, or we can't prove operator theory results using that because the setups are different. Like as soon as we go from sets to say the vector spaces, the dilation needs some tweaking. Okay, every time some modification is needed, but things are all look similar. So
yeah. So did you try to apply that, for example, to groups or monoids?
No. As I said, we haven't done anything. Means zero, other than what is there here. We haven't done for no.
Okay.
But it should be possible. Many things should be possible. Yes.
Hello, sir.
Yes.
Sir, Kalpesh here. Sir, I have a question. Can we do von Neumann inequality generalization in this setup? Is it possible?
Yeah, because we have no norm, so we have no contraction, nothing.
Yeah,
so how to interpret it? We don't know.
Okay, thank you.
We have no von Neumann inequality here.
Okay.
And if there is some way of making sense of it, okay, good.
Thank you.
Yeah.
So, hello, sir.
Yes, yeah.
Yeah, so you also stated an intertwining theorem, like a listing theorem motivated by Sarason. So, is there also some analog of interpolation theorems that can be set in this setup, set theoretic setting, and can be solved with that theorem?
No idea. I don't know. Interpolation, we said no. We don't know.
Okay.
So any other further comments or questions? Okay, so if there are no more questions or comments, let us thank the speaker for such a wonderful and interesting talk today. So I am out to Shine, the coordinator, if you want to make any comments.